Okay, so for the first couple weeks, we've been talking about making magma, and now we're going to move it to the surface and erupt this stuff. One of my biggest disappointments with this class is that I can't actually take you to this material anywhere. It'd be nice to actually show you how different melted rock behaves from other fluids that you're used to. You're thinking about fluids as dominated by water. Okay, that's the fluid you see. That's the fluid that you have the most experience with. Lavas don't behave like water at all. And what we'll spend some time doing over the next couple of weeks is talking about why, how, and how it actually affects the way these things erupt, when they erupt, how they erupt, volcanic behavior. So let's finish up with what we were talking about last class. We melted material last class. Now we need to move it to the surface. And moving magma to the surface is really difficult. It doesn't want to go. What are some reasons why magma has such a difficult time making it to the surface? We've talked about a couple. First of all, why does it rise? What's the driving physics behind magma rising? Why does it rise? Why doesn't it sink? Density difference. It's melted, expanded more than the rocks around it. So one of the reasons why it might not rise to the surface is that it has to be less dense than its surroundings, right? What happens to rocks, though, as you get closer to the surface? They're under less pressure, right? So they're able to expand a little more. So they're less dense as well. So as they rise, they tend to come in contact with lower density materials. And if at some point they don't get a density difference, then there's going to be no buoyancy. Why else might it not make it to the surface? Let's say this magma was moving through rock where it was always buoyant. It still might not make it to the surface. What else is going on that would stop that movement? Okay, yes, but why? What's happening to the viscosity as it moves to the surface? I mean, this stuff is really viscous, right? It doesn't flow very easy, but if it's buoyant and if it's molten, it'll have a tendency to rise. It'll just rise slow. But what happens to the magma as it rises? What else does it come in contact with? What sort of physical changes? What happens to rock as you move towards the surface? We talked that it becomes less dense. What else is different about the rock at the surface versus down deep? What's that? Temperature, it's cold, right? So what's its tendency going to be as it moves towards the surface? It's going to come in contact with colder rock, right? And that's going to affect the magma how? It's going to make it more viscous and eventually freeze it. So it has these two things sort of fighting against it. One is that the rocks are lower density near the surface. The other is that the rocks are colder. Both of those things conspire, think of it that way, to make magma not want to rise. It gets too stiff, eventually freezes, and it comes in contact with rocks of equal density, so there's no upward force on it. That's why most magma never reaches the surface. It's because rock density is generally lower. I don't think I put anything about temperature on these notes, but you can add that as well. So there always has to be a density difference. It has to encounter rocks that are denser for it to have a buoyant force. Now down deep, that's not a problem because the rocks down there are super dense. Near the surface, though, not so much. Especially if it comes in contact with sedimentary rocks. Sedimentary rocks are pretty low density. You think about things like sandstones, they have lots of pore space. They're not a dense rock. So if magma hits that, it's just not going to rise any farther. Now, a term I'll throw out because we will talk about this from time to time during the semester is diapir. A diapir is a large, and when I say large, we're talking about, if you're on the surface of the earth, mountain size or mountain range size. It's a big body of buoyant, rising melt that starts off in the asthenosphere and then eventually moves into the colder, more viscous mantle and eventually the brittle crust. And generally it takes the shape of, I don't know, like a hot air balloon. So it'll rise up through this plastic part of the mantle because it's buoyant. Eventually it'll hit the brittle crust. Most of it's stored in the brittle crust as dikes and sills and laccoliths and batholiths. And only a few percent ever makes it to the surface as a volcano. I think I have a diagram here. Kind of shows what that looks like. Yeah, so here's your typical subduction zone. So you've got your descending slab right here. As it descends, the minerals from that descending slab that have become hydrated over millions of years lose their water. That's what it's showing right there. That water lowers the melting point of the surrounding rock, induces melting. That melt collects in the sort of hot air balloon shaped material. They're less dense than the surroundings, so they rise up. But as they rise, they come in contact with colder material, which makes them more viscous. So they rise even slower yet. And eventually they encounter rocks that are cold enough to freeze them, especially as you get up here near the surface. The surface rocks are more brittle. They break, they have fractures. So a lot of this magma gets injected into cracks that either cut across pre-existing rocks as dikes. They squeeze in between rock units as sills. Sometimes they squeeze in between rock units and inflate and cause kind of a dome-shaped intrusive structure called laccoliths. But that's where most of the magma sits, down there beneath the surface. Then it'll just freeze solid. But every once in a while, we'll have the right conditions to actually erupt some of this stuff. And that's what we'll get to over the next couple of classes. Okay, any questions on this? Yeah.
So how is a batholith different than all this?
A batholith is actually a big diapir. So it rose up from depth into the crust, and it just probably encountered a rock of similar density and just sat there and cooled off over hundreds of thousands, millions of years, formed those nice big crystals that you see in granitic batholiths. So yeah, you can think of them as failed volcanoes. They were giant magma chambers at one point in time. They just didn't have the oomph to erupt. Mostly, every once in a while, you can find a batholith that is associated with an overlying volcano, but they're pretty rare.
They're not really good, but
These features move. Now, they rise super slow. We're talking millimeters a year, but you've got millions of years for this stuff to happen. We're geologists. You know, things can change at micro levels. You give it enough time, pretty soon you're talking miles, tens of miles. Give it enough time, that can happen. So this is kind of our conceptual model. Once we create the magma, it rises up and generally it stops. Okay, any other questions? Okay, what we're going to concentrate on next is what I was talking about earlier. What is this magma like in terms of its properties and how is it different than water? The fluid you're most used to. So we're going to end up comparing things to water quite a bit, okay? and really look at how magma differs from that one fluid that you know pretty well. Okay, so the next class and a half probably will be dominated by physical properties of magmas. And if you can understand what's going on with the properties of magma, you'll understand why volcanoes erupt, why lava flows behave the way they do, why lava flows have different structures on different surfaces under different conditions, why some volcanoes erupt explosively and produce ash flows. All of it leads back to how the magma behaves physically. So we're going to go back to sort of basic physics on this. Everybody had a physics course? Doesn't matter, because we're going to start at ground zero with the physics. So even for those of you who have had it, it'll be a review, but we'll get into stuff I'm sure most of you haven't had before, or you may have heard briefly in maybe structural, something like that. So don't worry if you haven't had any. All right, let's talk about what magma is again. We covered this real briefly, first class period or two. We've really been concentrating up to this point on the liquid. But magma is more than liquid. Magma can have solid minerals in it. If the magma temperature is lower than the melting point of the mineral, then the mineral will be a solid. A real common example of this is if you go to Hawaii, see those nice red runny lava flows. If you're able to get up there really close, you would actually see green olivine crystals, solid olivine in it. Olivine melts around 1400 degrees. These magmas are about 1150. So actually, they're not even close to being able to melt olivine. So olivine exists as a solid crystal. About 5% of the material in magmas are volatile species. Molecules where the boiling point is less than the magma temperature. Water is a great example. There's usually several percent water in these magmas because water boils at 100 degrees on the surface, more down deep, but not appreciably more. It's in the gas phase down deep. And then xenoliths, these hitchhikers, these solid rocks that get plucked as the magma moves from deep down, travels through rock units, little pieces break off. And if you go look at lava flows, most lava flows contain 2 to 5% xenoliths. You actually see these little chunks of rock in it. It shows you what the stratigraphy is below the volcano. Mostly it's just other volcanic rocks, but sometimes you'll see chunks of sandstone, limestone. It's pretty rare, but it can happen. So these are chunks of other material. And then going back to what we talked about last week, remember there's no single melting temperature for the mantle. Mantle has some garnet in it. It's got pyroxene, olivine. All of those minerals have different melting points. So you can't just say, oh, the mantle melts at 1300 degrees C, because the mantle doesn't melt at 1300 degrees C. Some of the minerals in the mantle start to melt at 1300 degrees C, but not everything does. So there's no one single melting temperature. And the same thing when these magmas cool off, there's no one single solidification temperature. You know, when we hit 1200 degrees or so, it doesn't become totally solid. There still maybe melted minerals that have lower freezing points than that. So it'll go through sort of a range of solidification. One mineral will crystallize in another. Think about Bowen's reaction series. You have to cool it off, and as you go through that cooling phase, different minerals start to crystallize. That's what happens with these magmas. All of these things, the liquid, the crystals, the volatiles, the temperature, all of them affect the viscosity. If you put crystals in your magma, it's more viscous than if it didn't have crystals. If you put bubbles in your magma, it's more viscous than if you didn't have bubbles. If you put xenoliths in there, that affects the viscosity too. Anytime you put something solid or you put a bubble in a liquid, it makes your material more viscous. And the more viscous material you have, the harder it is for gas to escape. And the harder it is for gas to escape generally means the more explosive your volcano is going to be. So we'll keep putting all of these concepts together until you kind of wrap your head around them. Any questions so far? Okay, we've focused on the liquid so far. Most of it's liquid. 90% of magma in general is liquid. Sometimes less is, obviously, as it starts cooling off, you have less and less liquid, more and more solids. But as liquid is rising up from the depths, it may have a couple percent crystals, maybe 5% volatiles, a few percent xenoliths, but 80 to 90% of it is liquid. And we've been focusing on liquid silicates. We talked about silicates a few weeks ago. You have these tetrahedron. And these tetrahedron like to bond to other tetrahedron. We call that polymerization, when you repeat these molecules and bond them together as you have here. So every magma we'll talk about, except one, which we'll get to in a minute, is going to have tetrahedron. And to some degree, all of the melts are going to be polymerized. And the more polymerized they are, the more chains and more bonding that you have, the more viscous your material is going to be. Now, as you heat it up, you break more bonds. It becomes less polymerized. So really hot magmas tend to be more fluid. As you cool it off, some of these tetrahedron can start linking together. The more they link together, the harder it is for those bigger molecules to move around other big molecules, and they become more viscous. So as you cool things off, polymerization increases. Eventually, you'll get to the point where solid minerals will start forming. And as you drop temperature, increase that polymerization, you get more viscous materials. So in general, more viscous materials form under colder conditions. And it seems kind of weird, I think, to people who start studying volcanoes for the first time, but colder magmas are more dangerous than hotter ones. If you ask, I think if you thought about it, anytime we associate heat with something, it has more energy, right? And you think of something being more energetic as being more explosive. With volcanoes, it doesn't work that way. The colder magmas are the ones you worry about more because they're more polymerized, they're more viscous, and gases can't get out. And gases are what drives this whole process. So try to keep that in mind. As you cool things off, things become more viscous, magmas become more dangerous. Okay, any questions on that? Volatiles can exist in your magmas in two ways. They can either be dissolved in your magmas, and when they're deep in the earth, they're generally dissolved in the magmas. And when they're dissolved, what they love to do is get in between those linked tetrahedron and break them apart. They like to break those bonds. That's one thing water does really well. When it's dissolved in a melt, it breaks those tetrahedrons. So what does that do to your viscosity? It lessens, it lowers it, right? So water, when it's dissolved in your melt, makes the magma more fluid, makes it less explosive. So dissolved magmas lower the viscosity. And you tend to get dissolved magmas when the magmas are really deep. As you lower pressure, volatiles tend to come out of solution and into bubbles. If you want a good example of that, go get a 2-liter bottle of 7-Up, right? You can look in there and you can't see the CO2 dissolved in the 7-Up until you shake it up and release the pressure on top. Then all of that CO2 that was dissolved in the liquid quickly goes in the bubbles and it just squirts all over the place, right? That's what happens with volcanoes too. So as you release the pressure, this water that's dissolved in your melt will eventually go into bubbles. The solubility drops, concentration exceeds the solubility, and you form bubbles. If the water is not melted, then these tetrahedron can link back together. What does that do to the viscosity? Increases the viscosity, right? It also forms bubbles. What did we say a minute ago about the presence of bubbles in a melt in terms of viscosity? Also makes it more viscous. So you sort of get a double whammy. When volatiles start to come out of solution, more polymerization increases the viscosity, and then the bubbles themselves increase the viscosity. And then those bubbles, what do they want to do? They're less dense than the surrounding. They want to rise, right? But they can't because the material is so viscous. So they kind of trap themselves in a way. Now I'm going to give you an equation. We're not actually going to use this equation this semester. I'll give you some other ones that we will use. There's an equation called the Einstein-Roscoe equation, and it deals with how viscosity increases when you throw crap in it. When you throw crap in your liquid, like bubbles or crystals. I'll just let you write this down, then we'll talk through it. Okay, just to sort of talk through this quick. So this term right here is the viscosity of your magma without any stuff in it. No crystals, no bubbles, okay? This term right here is the percentage of crystals or bubbles that are added into your melt, okay? So I gave you this example. If a magma has 40% crystals or bubbles, and you plug it into this equation, how much does the viscosity increase? You can play with this later. It actually increases the viscosity by an order of 10, one order of magnitude. I had a friend, he was got his PhD in volcanology and then went to work for a chocolate company. And he uses this equation all the time, actually, because chocolate has a viscosity, but a lot of chocolate companies put crap in their chocolate bars, like nuts, or if you've seen Crunch bars, full of those crispy treats. And he needed to calculate how much it would change the viscosity. So when they were squirting out the chocolate bars, they'd have to change the pressure in the chocolate squirty stuff in order to make the chocolate bar the right size. So he would actually use this equation and adjust his chocolate viscosity for things that he threw in it. Nuts, Rice Krispie treats, whatever. So all of those things increase the viscosity, and sometimes a lot. So 40% increase, that's a 10-fold change in viscosity or an order of magnitude. All right, any questions? Okay, so magmas get more viscous when they get colder. They get more viscous when water leaves the dissolved state because it no longer is breaking the bonds. And they become more viscous as bubbles and crystals form, which also happens as magmas cool. So magma cooling has almost like a quadruple whammy in terms of viscosity. It makes the magma thicker because water comes out of solution and bonding occurs. It makes the magma thicker because as you lower temperature, more bonding is going to occur. It's going to make the magma thicker as you make bubbles, as gases come out of solution into bubbles, and it makes the magma thicker as you add crystals, which form as magmas cool. So when magmas cool, their viscosity spikes dramatically. And when viscosity spikes, explosivity becomes more and more of a problem. Now we know how water behaves in magmas, but there's other volatiles as well. CO2, carbon monoxide, sulfur gases, hydrofluoric acid. There's even some noble gases that can come out. Only water has really been studied a lot because most volcanic gas is water, roughly 90%. CO2 is a few percent, sulfur is a couple percent, and all the rest of these are just trace. So we study water because it's the predominant gas. These other gases clearly affect the magma. We just don't really understand how yet. Water, as we talked about already, has a huge effect on magmas. Water is what lowers the melting point of the mantle and allows magmas to form in the first place. And then the viscosity of magma is affected by water that's dissolved in it, breaking bonds. And then when that water comes out of solution into bubbles, viscosity increases because the bonds can then reform, and the bubbles also increase the viscosity. Typically, we talk about volatiles as sort of one thing. We know most of it's water. Now, if you're able to look at magmas that are deep in the earth, we know that they have 5 to 7% volatiles at depth. And these volatiles are dissolved in the melt. Basalts, because they're so fluid, tend to more easily lose their gas. So if a basalt is able to rise from the mantle all the way to the Earth's surface, the pressure drops, those volatiles come out of solution, and they can escape because the magma is generally more fluid compared to the other magmas we'll talk about. So by the time they arrive at the surface, they only have maybe 0.5% or so gas left in them. Anybody know how we came up with this figure of 5 to 7%? We can't go down in the mantle, right? This is kind of cool. So we know there are minerals that form when the lava is really deep. Things like olivine are really stable under high pressure. And you can look at little crystals of olivine that are in your lava that erupts at the surface. And every once in a while, you will see a little inclusion of glass. They're called fluid inclusions. And they represent little bits of the melt that get trapped inside the crystal. So they're actually little remnants of the melt from when it was really deep. You can then blast those with an ion microprobe or some other cool piece of technology and see how much volatiles are in them. So fluid inclusions, melt inclusions, pretty neat things. We rely on them quite a bit to tell us the nature of magmas that are down deep in the earth. Now, rhyolites have a huge range of gas content when they arrive at the surface. Sometimes they arrive really degassed, 0.1%. Not enough gas to cause an eruption, so you get silicic lava flows and domes. But sometimes they arrive at the surface with pretty much all their gas. None of the gas is able to escape, especially if the rise is fast for some reason. And when it arrives with a lot of gas, usually anything over 1% or 2%, this stuff will explode. You guys have seen pumice, right? Yeah, if you look at pumice, 70% vesicles. And it's got a silica content of about 70%, which makes it super viscous to start with. And then the bubbles make it even more viscous. So this stuff does not flow very well at all. And in order to get it to inflate that much, you need a pretty high gas content, somewhere up in that 5 to 7% range. Most of the volatiles are water. All right, any questions? Okay. Just like with soda, we know that decreasing the pressure decreases the solubility. The gases come out of solution into bubbles. And then because the bubbles are less dense than the surrounding melt, they will tend to rise to the top of the conduit or the magma chamber or whatever the shape of the magma body is at that point in time. Sometimes, especially if you have a low viscosity magma like hot basalt, you can actually see the bubbles rise and pop in things like lava lakes or even lava flows. This particular set of pictures is from a volcano in Africa, Oldonyo Longai. It's not a silicic magma. This is melted carbonate rock. It's carbonatite. Completely different chemistry. It melts at about 500 degrees C, and it's got the viscosity of really thin mud. So gases can bubble up and escape really easy. This volcano almost never explodes because the gases escape so quickly because the material is so fluid. So this is actually liquid carbonatite in the day. If you look at this at night, it's bright red. It's like other lava. And at night, what happens is you don't get the light from the sun reflecting off the magma itself. When you do get that, you get the silvery appearance. So at night, all you have is the energy from the magma itself, red and infrared. So it looks just like red runny lava at night, but in the day, all you see is sort of the silvery, muddy looking appearance. It's neat stuff. Now, if you have more silicic magmas, bubble rise is essentially non-existent. It may take hundreds, thousands, tens of thousands of years for bubbles to rise up and get to the top of a magma chamber. Stuff's just too thick and viscous. Just won't get out of the way for the bubbles to move. Okay. Go through a little bit more and take a break. So I've mentioned eruption temperatures a few times. So these first three are all silica-based magmas. Komatiites have the highest eruption temperatures, 1400 to 1600 degrees. They were really common back in the Archean, several billion years ago when the Earth was hotter, had more heat. Now they're exceedingly rare. I don't even remember the last time a komatiite erupted on Earth. Basalts erupt between 11 and 1200 degrees. Rhyolites around 800. So again, as the temperature drops, more bonding can take place, more polymerization, more viscous. And then you add to that, on top of it, that as you go from komatiite to basalt to rhyolite, the silica content also changes. Komatiites only have 40 to 50% silica. Rhyolites have about 70. So rhyolites have lots of tetrahedron, and because they're colder, those tetrahedron link together. So they're way, way, way more viscous than basalts, which are way, way, way more viscous than komatiites. Carbonatites are completely different. They're melted limestone, melted carbonate. So they don't have tetrahedron. There's not much polymerization that goes on. So they tend to be very fluid. Carbonatites are wild things. They come out, they look black, silvery, muddy, and then about a day later, they turn bright white. As the minerals crystallize, it becomes carbonate again. But you see all these cool flow structures like spatter cones, lava flows. Some great videos on the internet of this thing erupting. I'll show you a few in a few weeks. We talked about this a little bit too. The more silica rich, the cooler it tends to be. The less silica rich, which generally also equates to high magnesium and iron levels, tend to be hot, tend to be more fluid. So hopefully you're starting to see a pattern here. I've talked about how these things affect viscosity enough times now that hopefully you're starting to get a sense that dropping the temperature, more bonding, more viscous, higher silica content, more bonding, more viscous, less water dissolved, more bonding, more viscous. Less water dissolved means more water in bubbles, more viscous. Colder temperatures, more crystals, more viscous. So pretty much any change a magma goes through is going to make it more viscous. Makes it harder to erupt. But if it does erupt, it tends to be more explosive. And we talked about this several times, that if you heat stuff up, you break those bonds, you get less tetrahedron hooked together. And if you cool it off, you get more bonding, you get more polymerization. And higher viscosities. All right, let's take 10 minutes or so and we will come on back.